So, hello and welcome to this slideshow. This is for subject big data, and the topic for me is big data science and software engineering. So, let's begin with it. First, we need to understand what is big data or big data science, as we say, is, and software engineering. All right. So, the confluence of these two disciplines is crucial for creating robust, scalable, and insightful data solutions. We'll come to that, which is integrated importance of these two disciplines. First, come to big data science or big data as we say. It is defined by the five V's as we understand it as volume, velocity, variety, veracity, and value. All right. The first one is the volume, the massive amount or the massive quantities of data that is being generated per second, be it from our mobiles, from online transactions, from social media platforms, from learning management systems, from all different kinds of applications running on the internet. It is the massive amount of data that's being generated. Velocity is the speed with which it is being generated. We, for example, take a transaction. It takes it 2 to 3 seconds to do a transaction, which is an online transaction. For example, we are, liking a post or sharing a post or watching a YouTube video. So it's the velocity with which the data is being generated. Variety is the different kinds of data. For example, on a social media platform, take WhatsApp. We, send photos, we send videos, we send voice messages, we send text, we send GIFs, we send, for example, docs from PDF, PPT, anything. So it's a different uh, variety of different types of data formats. Veracity, the quality and the trustworthiness of the data. Take, for example, on Twitter, we have several bots, which are, putting out the data, which doesn't have any significance. So, or, the data sets or the databases, they collect all sorts of data. And we need to make sure that the data that's collected and ingested in databases must be of the high quality so that we can, utilize the data later on. Is the value. When we talk about utilizing the data, it is what we mean by value. What's the value of the data? How can we utilize it? Take decisions to drive something to, foster innovation. So that is about the value and the five big V's of the big data. That's how we, understand big data in a major terms. Now coming to software engineering. Software engineering is another domain or discipline of, designing a product. It's a systematic approach to design, develop, and deploy, as well as maintain the software product or systems. It is the process or the process model, life cycle model that we follow while we are trying to develop a software product. It tells us about the rules, the regulations, and all the procedures and processes that we have to follow in order to get a quality product, which would be delivered in time and in budget constraints. It focuses on efficiency, reliability, and scalability, provides framework for big data infrastructure, how the data will be utilized, how and when we have to do things, and why. Ensures data governance and security, as well as enables automation of data pipelines. So that is in major overview about software engineering. Now, when we combine both of them, big data and the software engineering, this is where it comes to integrated importance. Integrated integration ensures that complex data science model can be implemented and operationalized reliably within modern high-performance technology ecosystems, bridging the gap between theoretical data models and practical applications. It also facilitates continuous delivery of data-driven products. In simple terms, it means that the big data platforms require a format and structure so that they can be implemented into high-quality software products, which is done with the help of procedures using software engineering lifecycle models. Now, let's understand the big data in certain depth, right? There are four major steps, as we can say. Also, we can derive multiple steps from within these four major steps. But as we take a major overview, these are the four steps: the data ingestion, the data cleaning and processing, data modeling and analytics, and data visualization and decision making. So these are the four big domains that we will be looking in. First, data ingestion and collection. The vast amount of data that is being generated has to be collected into a database or a schema, which is acquiring data from diverse sources, online transactions, social media, LMS, different applications running online. This involves defining data schemas and establishing reliable data pipelines to store the data in effective manner so that it can be utilized. Now, after storing data, we have to make sure that the data is of quality, it is of use. So that comes data cleaning and processing. preparing data for analysis, including validation, deduplication, transformation, and normalization of the data. The step is crucial for ensuring data is of a- approved and required quality and it is consistent so that we can utilize it later. Now, data modeling and analytics. The third step would be to utilize the data to model the data so that we can use it. Applying statistical models, machine learning models, artificial intelligence to uncover and discover hidden patterns to predict certain effects of about the data. So, it involves iterative model development and evaluation. It takes iterative models. We create and develop prototypes so that prototypes of the models, and we go about making trial models to apply different sorts of models so that we can acquire what we want. So such a prototype is finalized and it is then approved for production and data modeling. Fourth is visualization and decision making to communicate the results effectively to drive strategic and operational decisions. So what we do is we utilize dashboards and reports to visualize the data with model and provide it to people who do not understand raw data in terms of tables and in terms of information. For example, the stakeholders, the business people that run the company, they might not be that much capable of understanding the raw data. So we provide these insights that we modeled and analyzed in terms of reports and in terms of dashboards so that they can utilize it, understand it, and drive policy decisions. So this is a big in-depth overview about big data science or big data, which is extract the value from the entire data that is being generated. That's the whole point of big data science. You store the data, you clean the data, you model the data, and then you derive insights from the data so that we can utilize them. Now, we come to software engineering. We all know about the software development lifecycle models. It generally has 4 to 5 or 6 phases. The first is planning phase, the requirement gathering phase. Plan what software model, what software life process models will be using, the processes. Then we go for requirement gatheration, requirement analysis, functional, non-functional. Second, we do analysis. Third, we freeze the requirements and we go ahead with the work. Third is design. We design different data models, different schemas, and how the product will be looking, different prototypes about why and what will be the features of the application. Fourth is implementation. So finally develop the tasks, coding and all. The fifth is testing, main integration and deployment. We test the different modules that are being built and we integrate them. For example, the different modules that are built that are unit tested. And when the modules are integrated together, we do the integration testing. And after that, all this testing is done, we provide this system, running system, to the client, which is deployment or turnover. Now, sixth comes the maintenance, applying software patches, and keeping the software application up to date. Because there are different updates, different new technologies coming in the market every day, and you have to keep your system up to date. So it requires maintenance, general maintenance, and requires also updating software patches. So that's a big overview about software engineering in big data systems. Now, big data architecture and technologies. There are several architecture and several technologies, but we'll be taking a glance at 6 of them. And in those 6 domains, we have different technologies, working together. First, we have data architectures. In data architectures, we have data warehouses. Data warehouses, it keeps the data hot. So, what we mean by keeping data hot is that it keeps the data such that it could be retrieved in seconds, and it keeps entire amount of data such that it could be retrieved in seconds. So this is data warehouses, for example, data lakes. It stores structured or maybe unstructured data. It stores raw data in vast amounts for further enhanced analytics. We have data meshes, we have data lake houses. Coming to processing and analytics framework, we have Apache Spark, which is a unified engine for batch and streaming machine learning. We have Apache Flink. We have Apache MapReduce. MapReduce, provides a foundational model for distributed batch processing. We take a big task, we divide it into several different patches that are running on multiple thousands and hundreds of thousands of computers, which are running in parallel. So that's the work of MapReduce. We have storage solutions. We have Apache SDFS. We have Apache. We have NoSQL bases like Apache Cassandra, Apache HBase. We have MongoDB, and we have object storage like AWS S3. Then we have orchestration and workflow management, Apache Airflow, Apache Luigi. We have data governance and security, for example. We have Apache Atlas, for example. In AWS, we have IAM, Identity and Access Management. For Apache Ranger also, it is for security, centralized security administration, and fine-grained access control, just like IAM. For real-time data analytics and visualization, we have Apache Superset, we have Tableau, Power BI, Apache Hue, we have Grafana for time series data, and these are multiple tools for real-time analytics and visualization. Now, roles in collaboration spectrum of expertise. We can, understand it. For example, we take big data solutions architect. When a person becomes a big data solutions architect, when he can work in any of those domains, he will be called a big data solutions architect. Why? Because of course he has to be a software engineer, he has to be a big data engineer as well at the same time, as well as the data scientist. Why? Because software engineers and data scientists they can work on productionized models. Software engineers and big data engineers, they can work on infrastructure integration. Big data engineers and data scientists, you have to be to get to do the data modeling. So big data solutions architect comprises the expertise and skills of all those people. So that's a big data solutions architect for you. Now, coming to the challenges in big data software engineering. Of course, every domain and every engineering field will have its own challenges. First is data quality and heterogeneity. As we mentioned earlier, the data is growing exponentially, and to manage that inconsistent, incomplete, or dirty data arriving from numerous diverse sources, it is a complete and a constant challenge how to store and how to make sure that the data is of quality, which is in different forms, different formats. It could be structured, unstructured, anything. Second, scalability and performance as the data is growing. And what customer wants is performance. Within milliseconds, you have to provide the data back to the user. So that's a performance issue. That's a performance that user wants. And you have to scale every single day, every single time, whenever because data is growing exponentially. So you have to design systems, that maintain latency and high throughput even as the data grows exponentially. Then we have security and governance, implementing granular access controls like in IAM and anonymization techniques. Also, the data privacy regulations like GDPR, FCRA, CCPA, and then system integration complexity. For example, with the arrival of LLMs, every application has to have LLM for so that the user can query data and get to know more about the system. So that's a continuous challenge. There will be new methods, new technologies coming in, and they have to integrate it. They have to be integrated with the software system. So that's a continuous challenge. It also increases the complexity. For example, take an example of Netflix. So Netflix has a real-time data pipeline. For example, in AWS we have Kinesis data streams, which processes real-time data in parallel, and it provides recommendations thoroughly and at the same time. So you have to have a real-time data pipeline so that it can access what you're trying to watch, what you're searching for, so that it could provide recommendations in the real time. It maps, it tracks every user interaction from every play, every pause, every search, that too in real time. Then we have ML model, which is which is working in parallel to provide those recommendations, as well as we have to have operational efficiency so that they can work together and provide real-time insights. Future trends and innovations. We can never predict what will be the new technologies in the future, but we can take a hint and we can say will be having data meshes and composable stacks. The data would be decentralized, moving towards a domain-oriented data system, data ownership using modular interoperable components. Then we have AI and MLOps integration to automate the tasks that are being performed and increase focus on the machine learning operations, automate the deployment, the monitoring, and the governance of machine learning models, with which are running within the software systems. Real-time and edge computing, processing data closer to the user. For example, we have AWS Outposts. It is not possible to set up data centers near every single user. So you have to have local zones where the the density of the user base is high, so that you can provide some resources or some services near to the user, which is so that they have low latency and they can do things in real time with ultra low latency. And we have data centric architectures, for example, the businesses are now shifting from on-prem architecture to cloud architecture. So these types of data shifts will always be happening. Coming to the conclusion, we required essential synergy the big data science and software engineering discipline, they have to have combined so that we can develop reliable, scalable, and impactful as well as quality solutions. We have interdependent disciplines. Data science uncover patterns, build models, extract insights. Software engineering transfer these insights into production-ready systems, ensuring efficiency, scalability, and seamless integration. Cross-functional expertise, cause developing skills in both the fields is not only required but it's mandatory so that you can deliver quality systems and to drive the competitive advantage within the systems that are competing with your big data and software engineering system. So that will be all. That's a wrap, and thank you.